See you, gang. I gotta go.
Okay. Okay, we're going to we definitely want to do some more practice with chain rule, but I want to see if I can finish up our last set of notes. So implicit differentiation. So let's turn to page 9 in your Unit 3 packet. All right. So up to this point, all of our equations have been what we call, these are explicit equations. These are functions where every equation that we see is like f of x equals or y equals. There's never anything up to this point that we do with that y, right? It's always just y by itself. We never have y squared or y cubed or y within the equation. And that was to ensure that we always have functions, right? That we're always going to be able to pass a vertical line test. And most of the problems that we're going to do are going to be functions, where the x's and y's are nicely separated on either side of the equation. Like for instance, this, right? You have all your x's grouped together, and then it's always just y by itself. Today, we're talking about implicit equations. These are equations where x's and y's are either mixed together or something is a little bit, or something extra is done to that y variable. So for instance, if I had an equation like y squared equals xy minus x squared, this looks a little bit different than what we've seen before because one, we have multiple y's, and second, even if we didn't have multiple y's, there's y squared. And typically what's going to happen is you may have an equation that looks like this, right, where it doesn't pass a vertical line test. But we can still find a slope formula for equations that are not functions. Okay. And so really we're just, even with equations that are not functions, we can still find the derivative. We can still find a slope formula that will explain or describe how the slope is changing on that curve. Okay, so just for comparison purposes, let's find the derivative for both an explicit equation, which we've been working on all this time, versus an implicit, where we may have to do a little bit extra because of the fact that the y is not by itself. Okay, so let's find the derivative here. So y becomes y prime, but we also say that y can be dy dx. That just means I'm finding the derivative of y with respect to x. All right, 3x squared becomes what? 6x, okay, minus 27, yeah, x squared, and then the 5 goes to 0. All right. Now, I want to say that technically we are finding the derivative of this y variable, but up to this point, we never have to worry about anything addition. You know, it just feels like notation, right? Okay, y becomes dy dx, or y becomes y prime. But technically, we are finding the derivative of y because y is a variable to the first power. So y's derivative, just like x derivative is 1, so y's derivative is 1. So what we're really doing is we're finding the derivative of y, and then we're multiplying by that dy dx. So that's really the key that that's going to be different with implicit, is that sometimes our derivative may not just be a 1, it may be something else, but we're always going to multiply by dy dx whenever we're asking for y's derivative. So here we can see something's a little bit different about this equation. The y is not by itself, and there's also something done to the y variable. But let's just go down each of the terms here. What's the derivative of y squared? 2y, yep. So you treat it exactly like x, but because we are asking for y's derivative, we need to also multiply by what? Multiply by, what do we just see? dy dx, yeah. Okay. And then 5x becomes minus 5, and then equals, and the 4 goes to what? 0, yeah. Okay. So you may be asking, well, how come we don't do anything with the x's, but we do something with the y's? Technically, we are doing something with the x's. We are finding the derivative with respect to x. So technically, there's a minus 5 dx, but it just washes out because we're asking the derivative with respect to itself. So we never include that because it just always are just going to go away. So the only leftover that we have to worry about is the dependent variables with respect to the independent variable. And typically, it's usually going to be the y being the dependent variable. Now, after this, we just have to solve for dy dx. Before, we never had to solve for dy dx, was because y was always by itself, so it's always going to just be by itself. The derivative was always going to be by itself regardless, because everything was already on the right side. So the one additional step we have to take is algebraically add, subtract, divide, whatever it takes to get this variable by itself. So I'm going to add 5 to both sides. And then divide by 2y. So our derivative looks a little bit different because there's y's involved. Because the curve may look a little different, it does require maybe additional information so that we can pinpoint which point on the curve to ask about the slope. So that's why our derivative may look a little different. Derivative before was just in terms of x, but now your derivative formula may include the y because the equation just needs additional information so that it knows what point you're talking about and then to calculate the slope for you. Okay. So really, that's all we're doing today, just practicing with implicit. And we should be able to tell when to use implicit. Okay, you're not going to be asked, or you're not going to be told, okay, this one do implicit, this one don't do implicit. The way that we tell is we look at to see if there's something different about the y. Okay, either if you see multiple y variables, or you see something done with the y, like square root of y or y squared that you typically don't see, then you know that, okay, I got to do implicit, which means I got to find the derivative. I got to keep track of my dy dx's, and then afterwards, I got to move things around to eventually get my dy dx variable by itself. But your derivative, it's just doing the same thing as all derivatives do. It's just describing how the slope of this graph is behaving at any moment in time. Okay, so let's do some more examples here. These are the steps that we just kind of talk through. We just find the derivative. Every time we come across y's derivative, we need to multiply by dy dx. And then after that, we're just adding and subtracting to eventually get that dy dx variable by itself. Yeah. Thank you. Okay, so let's try sample one. Give me a moment. All right, so let's try this one here. All right, x squared minus 2y cubed plus 4y equals 2. Um, every term is just power rule. And we know there's implicit involved because there's something, we see y is out of place, right? And we see multiple y variables. So you know that there's going to be some dy dx's that pop up. Okay, so let's go down each term. X squared becomes 2x, good. Minus 2y cubed becomes we are asking for y's derivative, so we also need to include what? Times dy dx. Yeah, we need to include that derivative variable. Plus, okay, what's 4y's derivative? Just 4. We are asking for y's derivative, so even though the y disappears, we also still need to include a dy dx. Equals what? 0. Sometimes I see students think of that 2 as just on the other side, so it's not getting impacted, but both sides of the equations are getting impacted by our derivative, so that 2 is not going to stay. That 2 will go to a 0. Or I see students, they feel like they only need to include dy dx if there's a y showing up. But it's more like where, is there a y to begin with? If there's a y to begin with, then we should be expecting dy dx. So another way that I think may help is if you look at your original equation, count how many instances of y's that you see, right? You see there's 2 different instances of y's. So at the start, because the equation starts with 2 different y variables, we're going to be expecting 2 different dy dx's. So don't depend on dy dx from the derivative. Make your decision based off of how many y's you see at the beginning of the problem. That's how many dy dx's will show up at the derivative level. Okay, so now we're basically at the derivative level. Now we just have to add and subtract in a way where we can solve for our derivative variable. Now we can also call this y prime, but I prefer dy dx because sometimes y prime looks like y to the first power, and that kind of can look a little confusing. So I think dy dx is more descriptive, and it's also just easier to spot. Okay, so we're going to collect all the dy dx terms on the left side of the equation. So I'm going to leave these 2 on the left so I can eventually factor that dy dx out. I'm going to go ahead and subtract that 2x over to the right side. Now, there may be other common factors, but we only want to factor out dy dx because that's really the only variable that we care about getting by itself. So I'm going to factor dy dx out. What's left is the negative 6y squared plus 4. Okay. Finally, we can divide the parentheses over to the right side, and we just want to get our derivative variable by itself. So now to find the slope of this curve, the derivative is going to need both the x and y variable order pair, the full order pair, in order to locate the slope of this curve. And again, the reason why that happens is because if the graph doesn't pass the vertical line test, which usually it doesn't, this may not be what the graph looks like. If I just give it the x value, if I just say, at x equals 2, it's not going to know which x equals 2 you're talking about, right? Are you talking about this point or this point? So it needs both the x and y value so that it can pinpoint, okay, you want this point, okay, I can find the slope at this point. Or if it's this point, then it's going to be a different slope. So that's why the derivative looks a little different with implicit. It just needs additional information because it doesn't know, sometimes it may not know which point you're talking about. All right, let's go to next page, page 10. Now, implicit is not too bad, but sometimes it can get more complicated because there may be other rules involved for certain problems. Let's look at example 2 here. 3xy cubed minus 2y equals 7. So first, I want us to look at this and realize, okay, this is definitely implicit because there's something strange about the y variable, right? It's not how our problems have looked like in the past. So we need to be able to look at a problem and say, okay, that's implicit because something different about the y variables. So we definitely want to do power rule, but something else here. Can you spot another rule that we have to involve? Has to do with this 3xy cubed. What other derivative rule do we have to make sure we include as we find that derivative? Right, how many variables do you see here? 2. How are they related? Multiply. So what happens if we're trying to find the derivative of terms that are being multiplied with each other? What rule do we have to use? Product rule. Yeah. So it sometimes kind of flies under the radar a bit because we may not recognize it, and we may say, okay, well, 3x is 3 and y cubed is just 3y squared dy dx. We have to realize, okay, these are two different variables. These are being multiplied together. I have to go through a full product rule just for that portion. Okay, so it doesn't really announce itself. We just have to be able to see it and recognize, okay, I got to do implicit, but I also have to do product rule because these are two different variables and they're being multiplied with each other. So I'm going to label what I'm going to do here, f and g. I'm going to assign that 3x to be my first term, and I'll assign y cubed to be my second term, and I'm going to go through a product rule here. So this f prime g plus f g prime is just to build out this derivative. And after we get done with that, then we start to make sure we finish off the rest of the equation's derivative. Okay, so let's go down this one by one. Okay, so f prime is asking for the derivative of 3x, which is what? Just 3, okay. All right, g function is the original g function, which is what? Y cubed, okay. Back to f, the original f function, which is 3x, okay. G prime is asking for the derivative of y cubed, which is what? 3y squared, okay. Anything else? Good. Anytime we're asking for y's derivative, we also need to include that dy dx to indicate that we are finding the derivative of this dependent variable. All right, so now that completes product rule just for that portion, but we're not done yet. We still have to finish off the rest of the equation. Okay, minus 2y, what does that become? Anything else? Good, dy dx. Even though the y disappears, we are asking for y's derivative, so we do need to include that dy dx. Okay, again, we count two different instances of y's, so we at the beginning of the problem, so we should be coming out with two dy dx's. Equals, good, the 7 is not immune to the derivative process. It is also getting impacted. That 7 goes to 0. So that completes the calculus portion. The rest is just collecting dy dx's, grouping them together, factoring it out, and then solving for dy dx. Okay. Any questions so far? A common question that students have is, well, how come this y squared has dy dx, but how come this y cubed does not? How come we don't do dy dx for this variable?
So we're not asking.
Good, because we're not asking for the derivative, right? If we're not asking for the derivative, then there's no dy dx. It's just asking for the original expression. So it depends on where you are in product rule, right? Only when the derivative is called on are we going to involve potentially that dy dx. All right, so now I'm just going to clean up. There's really only 3 terms here. I know this looks like a lot of things going on, but this is just one term. So I'm going to clean up first before I move things around. So I just want the dy dx terms on the left side. So I'm going to subtract the 3y cubed over. Again, there may be other factors, but we only care about trying to isolate that dy dx. All right, divide both sides by the parentheses. Okay. Again, our derivative is just naturally going to look a little messier, but the big picture remains the same, right? This is just describing the slope of whatever this graph looks like. If I want to figure out how the graph looks at order pair 1, 3, I just plug 1, 3, assuming that 1, 3 is on the original equation. Plug in whatever order pair that lives on the function, on the equation, sorry, and then that will give me a number, and that number will describe how steep this curve is at that point. Any questions so far? I do want to point something out here. Now, if you present your derivative without everything factored out and cleaned up, that's fine. Okay, you don't have to. If there are common factors that let's say there's a 9xy squared minus 3, you can factor 3 out and reduce. You don't have to reduce. If this free response, you can leave your answer unsimplified. AP exam accepts it as well. But it is kind of good to know how to clean up and factor and factor and reduce, because if it's a multiple choice question, then typically your answer choices are going to be reduced all the way through. So that's one thing to consider. The second thing is that you may arrive at your answer. This is really only applicable for multiple choice. You may arrive at your answer and realize that it doesn't, even if it's reduced, that it doesn't show up in your answer choice. And that may be because your signs are a little bit different. And I say that to collect your dy dx's on the left side, but you don't have to. You can collect your dy dx terms on the right side, but your derivative may come out to be a negative version of the original. So let's say this was what you got, but your answer choice looked like this. So are these the same thing? They actually are. They look different, but they're the same. Why are they the same? Yeah, so if I can multiply my numerator and denominator by -1, right? If I multiply numerator by -1, I'm essentially multiplying by 1, right? And so if I can multiply my numerator and denominator by -1 and get to a different version of the answer, that they're going to be equivalent. Okay, so I just want to kind of share that with you, because if you're coming across your answer, but then your answer choice is not showing up, it may just be off by -1. So if you want to create a different version of your answer, just multiply your numerator by -1 and your denominator by -1 and see if that will allow you to spot the variation that they're showing up in the answer choice. Okay. But if it's true response, you can leave your answer in this form or this form. The graders will have to accept both versions. But this is really only for if you're trying to match your version with the answer choices version. Okay, example 3 is really a preview into the next unit. It says differentiate y squared equals 5x with respect to t. Now, everything that we've been doing so far has been with respect to x. X has been our independent variable. But let's say there's a variable t that we don't see in the equation, but that is now the independent variable. So this is going to kind of go into next unit, which is related rates. The idea is that we're going to find the derivative of each variable, but with respect to t instead of x. So now instead of dy over dx, now we're going to get dy over dt. Okay, and that x before was the independent variable, but now t is the independent variable, which means that every variable, including x, is getting impacted, and it's going to have that derivative notation that shows up. So in this case, y squared will become 2y. And because we're asking for y's derivative with respect to t, we just include that derivative variable. And now x is no longer the independent variable. 5x would become 5. And we're asking for x's derivative with respect to t. So we say dx over dt. Okay, we'll talk about next unit, what this means, how this applies to the problems that we're going to solve. But this is just kind of a preview into, okay, this is, still implicit sort of, but if we specify a different variable t, then that's what's showing up in the denominator. Okay? That's not going to be this unit. This unit, if it's implicit, is always dy over dx. All right, I'm just going to have us practice implicit. So let me start you off with an easier one, and then we can look at one that's maybe challenging because of the signs. So let's try number 4. Can we? Wait, hold on. Let's try number 4. Okay, so this is on page 11. So the direction says find the derivative, find dy dx. Okay. How do we know by looking at this equation that we have to do implicit, even if we're not told to do so? What gives it away? Yeah, that y variable, right? The y is not by itself, and there's something done to the y. y cubed, y squared, square root of y, multiple variations of y, we should be able to look at an equation and know, okay, all right, this requires implicit. All right, so try that. Go ahead and find the derivative of each term. Really, the only thing that you need here is power rule. And then once you find the derivative, then you should have one dy dx that shows up. And then you're just trying to add and subtract in a way where eventually you can isolate that dy dx variable by itself to get to your derivative equation. Again, I say you don't have to reduce, but I'm just going to reduce it. Yeah, so even though I will accept this answer, I do want us to practice reducing it just for multiple choice practice, just for multiple choice matching purposes. All right, are we good with 4? All right, number 5. We see that there's a need for implicit. First off, there's y squared, and then there's also multiple y's. But something else. What else do we need besides power rule? Product rule. Yeah, I know that sometimes it kind of hides itself, right? It doesn't announce itself that there's product rule, but these are definitely two different variables. We can't merge it into the same variable. They have to stay multiplied with each other. So we have to go through product rule. Now there's something else that is causing issues with our process. What do we have to be careful about as well? What's potentially troublesome about this equation if we're not careful? The negative. Why is this potentially an issue that could cause a mistake? So when you go through product rule, it's f prime g plus fg prime, right? What is that negative going to have to do with that f prime g plus fg prime? It's going to have to distribute. Okay, so that negative sometimes is a cause for issue. I mean, if you let that negative be part of the x value, then that's fine. But I typically what I do is I put a parenthesis around that xy as a reminder that when I go through product rule, I'm gonna still have to resolve that negative in front and distribute through. So there's not an issue if it's x cubed plus xy, but that minus xy, the issue is your signs may be off with that second term because you may forget to distribute. Okay. All right, so I'm going to set this up here. So x cubed becomes 3x squared minus, I'm going to do my whole product rule in a set of parentheses, and then I can worry about distributing that negative through. All right, so this whole space is just to take care of that xy. Okay, f prime times g plus f g prime. Okay, y's derivative is 1 dy dx. Okay, I'm going to just distribute the negative through, and then once my parentheses are cleared, I can collect my dy dx terms together and then work towards solving for dy dx. But at this stage, we're done with the calculus. Now we just have to do some cleanup. Okay. I'm going to collect my dy dx terms on the left side. If you don't collect your dy dx terms on the left side, collect on the right, your answer will just be a negative version off of mine, which is fine. Okay, so after we get the negatives, parentheses resolved, I'm just grouping my dy dx terms on the left side. I'm moving all the non-dy dx terms to the other side of the equation. That way I can factor my dy dx out. And then I divide over. This is now my slope formula. Questions? Now, every time that we learn a new rule, there's always going to be a find equation with tangent line. So we're going to do that as well. So next page, we're going to find we're going to find the derivative using implicit, but we're going to take the order pair, find the slope at a specific point, and then do point slope form. So let's go to the next page and just practice that process. Okay, let's try 21. Wait, change my mind. 25. Let's do 25. Okay, we could distribute this through. But I'm just going to leave it in this form and just go through product rule. And we know there's implicit because we see y is not by itself. It's mixed in with our equation here. This is only asking for the slope. So after we find the derivative, we just plug order pair 2, 1 in, and we get to the slope. I'm just going to subtract that 2xy over to the right side. I'm going to divide that x squared plus 4 over. Okay, so this is my derivative. I got to go one step further. I want to find the slope at this specific location. So the way that you want to indicate that you want to find the slope at a point when there's an order pair involved, typically we just say f prime of 2, right? Or f prime or y prime of 5. Usually our function only requires the x value to find the slope, but now we need the full order pair. So the notation that you're going to typically see to indicate that you want to plug an entire order pair into the derivative, you'll say dy dx and you'll put a vertical bar, and then you'll put the order pair that you want to plug in, and you say equal. So that just indicates that I want to insert my full order pair into the derivative. It's basically my implicit version of saying f prime of 2, but it just requires a full order pair. So that's why it looks a little bit strange with that 2, 1. So now I can plug in, replace every x with 2, replace every y with 1. So whatever this original graph looks like at order pair 2, 1, this graph is going to be experiencing an exact steepness of -1/2. Okay, one last problem, 51. Now 51 is asking for our full equation of a tangent line. So we're going to get to this place where we get to our slope, and then we'll take our order pair, and then we'll do point slope form. Okay, so let's try 51, and let's see how far we can get. Again, we know there's a need for implicit because there's something done to the y variable, and it's not by itself. Okay, so the radical rewritten as rational exponents to get it ready for power rule. We go through power rule. Dy dx will show up. Don't forget that 5 is also getting impacted. That 5 will go to a 0. Pushing the exponent variable to the denominator. It's easier. Oh, I think it's cleaner to think in terms of positive exponents and negative exponents. And once I do that, I'm just going to subtract that x over to the right side so I can eventually get that dy dx by itself. Now that left side is still 1 over 2y to the 1/2. But I know that dividing by a fraction is the same thing as multiplying by the reciprocal. So I'm just going to take that reciprocal of 1 over 2y to the 1/2, make it 2y to the 1/2 over 1. And that cleans up nicely now. My derivative is just negative square root of y over square root of x. So now that I have my slope formula, I can take my order pair, plug it in here to get my slope. Once I have my slope, take my order pair, my slope, and do point slope form. So I decided to clean up a little bit to make it easier for me to plug in. So I made my dy dx negative square root of y over square root of x. And now I want to indicate that I ready to plug in my order pair 9, 4. So I do a dy dx, vertical line 9, 4 to indicate I'm going to be plugging that 9, 4 into my derivative to get to my slope. negative 4 to the 1/2 over 9 to the 1/2. That's really square root, right? Square root of 4 is 2. Square root of 9 is 3. Here's my slope. There's my point. There's my slope. Point slope form. Okay, you guys have homework for implicit. We're going to start going. The rest of this packet is mainly review. So we're going to start reviewing on Monday. Your test is going to be on Friday. I hope to get back your quizzes by Tuesday. If you look on the board there, far left, I have help sessions Tuesday morning, Wednesday morning, and Friday morning. I'll definitely send out reminders as we get closer. Homework over the weekend, I'll send out a reminder on Sunday. I'll be checking homework on Monday. All right, come get your phones.